I would like to welcome you to the medal lecture of the 2013 Dominique Cassini Medal. And as most of you will be aware, this year's medalist is Roger Bonnet. And I'm really delighted to have Roger Bonnet here and deliver the medal lecture. Roger Bonnet is, of course, very well known in the field, and there's no need for introduction for most of you. So very briefly, Roger Bonnet has had a very fruitful, very energetic life and has contributed immensely to our disciplines, among many other things, as a director of the science program of the European Space Agency. He has established a long-term program, Horizon 2000. He's been very much involved at the French level also in space science. He's reorganized and provided advice to reorganizing space science in France. And he has been a prolific author with almost 200 publications, journal articles, and books. Roger Bonnet has already received many distinctions and awards, and they literally fill a full page or more, including many prizes, awards, honorary doctorates, a couple of honorary doctorates in various universities around Europe, and also membership of learned societies and academies such as the Swedish Royal Academy of Sciences. And I'm now really looking forward to the medal lecture of Roger Bonnet. Please, the floor is yours.
Thank you very much for the introduction. Thank you. I appreciate very much. This lecture will be for my non-European colleagues' lecture given here to describe you how, in severe financial times, how you can overcome the situations and be optimistic about the future. In the past 50 years, thanks to space research, we have accessed the most extremes of vacuum, of density, of temperature, of gravity, and of time, thanks to space. We have discovered black holes everywhere by thousands, confirming in an unprecedented way the predictions of the Einstein theory of relativity. We have discovered water everywhere also, in the universe, on Mars, Europa, and the moons of Saturn. In the past 50 years, we have extensively traveled through space, through the solar system. We have landed on the moon, on Mars, on Venus, on Titan, and on asteroids. With the pioneers and the voyagers, we are reaching the limits of the unexplored, of the heliosphere, and we will explore the virgin territories of this space very soon. Maybe even more essential, especially for the attendees to these conferences, has been the revelation that space observations of our own planet represent one of the most promising tools ever invented to serve humanity on Earth. Let me talk about how this all started as far as I am personally concerned. And I apologize if there is a lot of reference to my situation, but I think it's an example for the young people which I think is probably useful. Nothing in my early years would have indicated what my professional life would be. A particular event, however, changed the course of my life and literally put me on an orbit which I never abandoned since then. That was on the 4th of October 1957. I was passenger in my father's car on the Boulevard Arago, not very far from Rue Cassini in Paris. A beautiful boulevard, as you can see, where I have decided to live until now, and I was surprised to find on Google a picture of my apartment. When the radio announced in the car of my father that the Soviet Union had launched the first artificial satellite of the Earth, I was stunned for two reasons. First, that the Soviet Union was able to do it. At that time, it was not considered as the most advanced technological country in the world. Second, that it was possible to detect and even listen to a signal coming from an altitude that no one has ever before reached, emitted by an object circling the Earth at a velocity of 29,000 kilometers. I was very excited. As a young guy, I was less than 20 years old, about this unbelievable prowess, and dreamt of also reaching the stars above myself. In fact, my extraterrestrial excursion eventually aimed at only one star, the biggest in the sky, the Sun, which you can see as pictured today by the SDO satellite of NASA at probably 9 o'clock Vienna time, and you see what the star of my entire life has been. Several personalities, scientific personalities, helped me responding to the challenge of realizing my dream. First, Avery Schatzman, my professor at the university and the father of many students and scientists and astrophysicists. I took the picture myself at Nancy University when I was a student, when we visited the Nancy station. Jean-Claude Pecker, his friend and colleague, who wrote a book with him. Jacques-Émile Blamont, who would later become my boss, who was then the rising star above the horizon as a great spaceman in France. And finally, his former boss, Alfred Kastler, Nobel Prize in Physics in 1966. Each one, in their own style, had a determining influence not only on my scientific orientations and then evolution, but also on how to interact with human beings in different ways. These four great scientists formed, in fact, the group of four of my thesis PhD jury, kind enough to assign me the title of Doctor in Sciences on the unusual date for Paris University of the 19th of July 1968, as you can recognize the event. And you see the picture of Alfred Kastler here. Just here to mention that he was a great negotiator between the revolutionaries of 1968 and the police, and played a very key role in piecing all these people. I would like to thank him as chairman of my jury thesis and all the three other colleagues which I mentioned for having granted me this PhD degree, for having uncovered some yet unknown phases of the Sun and of its UV spectrum observed above the Earth's atmosphere by means of rockets and balloons. The rocket which I used, called Véronique, a French version of the V2 rocket, was launched from Hamagir, some 1,000 kilometers southwest of Algiers, near the border with Morocco. There I had my first encounter with two other extraordinary men, Gerhard Terendel, whom I think is in this room, and his boss, Reimar Lust, whom you see here at the large-scale picture of this slide. This period in my life will remain the most pleasant of my scientific career, for the reason that I was given the opportunity of living at the start of the space era, at the age of all dreams. I could realize a dream, and I encountered many unique people, like the one whom I mentioned, and many others. And I had an enormous amount of luck, leading to discovery and recognition from my peers. In the wake of the 1968 events, I was given the responsibility of directing the newly created Laboratoire de Physique Stellaire and Planétaire, which is now called the Institut d'Astrophysique Spatiale in Orsay, whose program centered on solar physics, astronomy, and planetary exploration, where the average age of the technicians and the scientists, that was in January 1969, was somewhere between 20 years old and 30 years old. I was the eldest, and that is why I was asked to lead this group of protesters, or contestataires, as Blamont liked to call them. In parallel, I was increasingly involved in European space science, first in the working groups of ESA, advising the ESA system, the SRO system, and then of the European Space Agency, the successor of SRO. At that time, it was enough to know how to mount a grating or a mirror on a rocket to become a world expert in space engineering and space science. So I was called in these committees, and I was, of course, certainly very well advised by several people, among them Otto Kippenheuer, the famous solar physicist, Kees de Jager, who would become the president of COSPAR later on, and Jean-Claude Pecker, my mentor. And then led me to become more European than French. I also experienced the Council of the European Space Agency and SOHO, and the need to reach consensus on decisions after lengthy discussions, iterations, fights, compromises, usually reached overnight after long debates. I won't go through all the details of that period, but let me just mention the determining invitation made in 1977 by André Lebeau, here, who was then the ESA director of future programs and planning. And André Lebeau, unfortunately, sadly passed away a few weeks ago at the age of 80 years old. André Lebeau invited me to take the chair of the then called Scientific Advisory Committee. In this group photo, you see this committee on the launch pad of the space shuttle at a visit that we made in 1978 at Cape Canaveral. And the Scientific Advisory Committee was a committee that advised the ESA Director General on all scientific matters, including space science, earth sciences, meteorology, microgravity, and life sciences. I accepted the invitation to become the chairman of SAC. It was a challenge. I was a little bit afraid, but that was probably another of these key events which determine the evolution of one's professional life. One most important task assigned to this committee was to formulate a long-term plan in space science in view of the forthcoming development of the Space Shuttle Space Lab system, so-called STS, Space Transportation System, and of the forthcoming Ariane launcher, the European rocket. With a budget which was then less than 1/10 the equivalent budget of NASA for doing the same science, ESA had no other choice than establishing priorities and identifying them for several budget cycles over at least 10 years. The aim was also to attempt reverting the financial stagnation of the ESA science budget, which had been flat for since the beginning of ESA and the transformation of SOHO into ESA, that is to say since 1973. And there was very little hope that this budget would increase. So with the help of a member of the SAC, Klaus Pinkow, we worked very hard to publish a plan which was presented to the ESA Council in 1979. The Council listened to me politely, but did not give 1 penny more to the science program. Well, I was a little bit shocked, if not disappointed. They were short of cash in the European member states, and we, of course, did not offer them any idea where the priorities were in our green document. We just listed a wish list. And they did not know how much it would cost them and how much they would have to pay for the national contribution to the payloads of these missions, which are on top of the contribution of the various elements of the spacecraft. That missed opportunity remained in my memory when a few years later I happened to be elected by the same council, the successor of Ernst Trendelenburg, the ESA director of the science program. The position was opened for applications in the second half of 1982. And for me, leaving a very active scientific position, which I had for nearly 20 years at CNRS, to become an administrator of science was not, I tell you, an easy decision. I consulted several of my colleagues and mentors, Pecker, of course, André Lebeau, Hubert Curien, then Minister of Science at that time, Henk van der Hulst, Kees de Jager, and of course Reimar Lust, who would become the next Director General of the European Space Agency in 1984. The general advice of these people was that I should compete. Then I decided to compete. In the course of the interview by a board chaired by Eduardo Amaldi, here on this slide, in his capacity as chairman of the Science Program Committee of the European Space Agency, I decided to present myself as a scientist and not as a future potential administrator, because I had no experience at all. I explained to this board, in which Curien, de Jager, and the ESA Director General, Eric Quisgard, participated, what I had done and achieved at the CNRS, at the LPSP, and at Service d'Aéronomie before, over the 20 years that I worked at CNRS. Knowing the great interest for Amaldi for particle physics, he was, in fact, Amaldi was with Pierre Auger, the founder of CERN in Geneva, back in 1953, I think, just after the war, just to make sure that science could be established among all European countries to build up an instrument of dialogue between the previously warring countries like Germany, France, the UK, and so on. So I decided in front of Amaldi and the board to describe the work which I was doing at that time with my colleagues Philippe Delache, Eric Fossa, Gérard Grec, Klaus Fröhlich, and André Balog, who might be in this room today, and I would like to thank him for that. On the definition of the phase A, definition of this mission, DISCO, which meant Dual Irradiance Solar Constant Observatory, on which we wanted to measure the solar oscillations. And in fact, this mission was not selected, but gave birth to the SOHO satellite, which was carrying a payload dedicated to helioseismology from space. I explained to Amaldi and the group how helioseismology will help solving the then very intriguing problem of the missing neutrinos. There were only a third of the neutrinos emitted by the sun which were collected by the detectors on the Earth. And in fact, indeed, helioseismology contributed to solve this enigma. From that point on, in the interview, the discussion was essentially dealing on solar neutrinos between Amaldi and myself. And that was naturally concluded by my becoming, on the 1st of May 1983, the successor of Trendelenburg. You may recognize him on the right-hand side, a position that I would hold for 18 years, beating a record of the longest man in the same position at ESA. In the few months that preceded my entry in function, I had several discussions with the scientific community and with my future collaborators at ESA. Among them were Johann Blecker, on the left, and Vittorio Mano from the European Space Agency, who was the secretary of the Scientific Advisory Committee, which has been renamed SSAC, Space Science Advisory Committee, restricted to only space science, and Johann Blecker, who was the chairman of that committee. These two persons were very instrumental in the development of the so-called Future Horizon 2000 program, which I will describe now in its genesis and in its content. The need to establish a program of missions at ESA came out frequently through the discussions I had with the scientists at this time, even though the approaches necessary to establishing such a program were totally diverging. As a scientist, I knew that the first step in that exercise was to consult the scientific community first, in order to probe their interests and their ambitions. This was done in earnest in October 1983, a few months after I took my duties, and we consulted the community. We asked them to provide concepts of mission, and we received some 77 concepts of mission. The community was not very sure that this was useful, but nevertheless they responded because they wanted to help, and the community helped a lot. These missions covered all fields of space science, astronomy, planetary science, plasma physics, solar physics, and even Earth sciences. Johann Blecker and I formed a survey committee trying to frame this program, which was chaired by Blecker himself. And overall, some 50 scientists were involved in the various committees and panels which were working for this survey committee. And in less than 6 months, we were ready to establish priorities and set up the program. That was done in the inspiring and beautiful, though very cold city of Venice in the early days of June 1984. The philosophy that inspired the establishment of this program rested on a blend on several factors, 3 main factors. First, ambition. The ambition was to give Europe its independence from the United States. Sorry for my American friend, but that was the reason why we wanted to have a program which Europe could do by itself. While at the same time developing first-class missions, so-called flagship mission in today's jargon. That sense of independence was exacerbated by the fact that a few years before, NASA had decided on its own decision to cancel one of the satellites of the 2 satellites mission called out of ecliptic mission, now recalled Ulysses, whereby 2 satellites would orbit the Sun perpendicular to the ecliptic plane, and one would take picture of the Sun, measure the environment in the heliosphere, and the other one would be complementary. NASA canceled the most important instrument with telescopes and optical systems, and this was a great crisis at that time between Europe and the United States, leading in fact to managing later on the space station through not anymore a memorandum of understanding, as was the case for this out-of-ecliptic mission, but through an intergovernmental agreement. At the same time, this little rocket, Ariane, in its first version, Ariane 1, was modestly and successfully showing that Europe can really become, at its turn, a leader in space activities and hopefully in space science, resting on its own means. The program also had to be realist with respect to the financial resources of ESA and its member states, and my earlier experience, which I described to you when showing the green books to the Council on the SAC long-term plan back in 1978, contributed to my own imposition of restricting the ambitions of the science community to missions that Europe could afford alone, without, however, abandoning the possibility of increasing the scope of these missions later on through international cooperation. At the same time, recognizing that the ESA member states were ready to start the development of Ariane 5, of Hermes, a small European shuttle carried on top of the Ariane 5 rocket, and later on of the International Space Station with NASA, a small increase in the scientific budget did not seem to be out of reach. The third factor, which was very instrumental in defining the structure of this long-term program, was the science policy aspect. I was very sensitive to this, being the head of a big laboratory in France. In fact, that I was impressed by the fact that the European scientific community had acquired a substantial and competitive expertise in several domains of space science, such as X-ray astronomy, infrared astronomy, comet science, plasma physics, and solar physics, mostly through cooperation with NASA and with the Soviet Union at that time. And relatively large groups of scientists all over Europe had emerged in these fields, supported by their countries nationally through important investments and infrastructures. Equipments, which created major facilities that were able to build instruments and develop the necessary hardware to put on future missions. So this offered unique opportunities in the European areas of excellence, which I just described, and I thought that these investments had to be preserved and exploited. These 3 main considerations naturally led to a program structured on the 4 major elements, which you see here on this diagram, which shows this big element, the cornerstones in red cubes, which were all definitely accepted. No more competition between these elements without further recourse to destructive competition. And that offered a double advantage: preserving the science community in its areas of excellence, and second, providing a cost-efficient and focused approach to the development of the new technologies which would make these missions possible and implementable. The program was to be completed in about 20 years. And in addition, medium and small size missions, as you can see in the blue cubes, including, in fact, the past missions. I will comment on that later. They were introduced, these blue blocks, as indispensable elements of the program in order to maintain flexibility. And these missions would be selected constantly in competition, regularly, and not in order not to freeze the community in just 4 big missions. It required what we call at the time a modest increase in funding requirements. Our assumptions was to reach a cruise level of funding after 10 years for an annual increase of 7% in real term of the budget. This is just unbelievable today, but this is what we presented to the Council of ESA. The second element in this building of the Horizon 2000 program was the management approach. It's good to have a program, and how do you implement it? First of all the elements had to be designed to cost. All elements of this green, the big boxes, the red boxes, had to stay within a budget. And I was very strongly inspired by my Japanese colleagues who were working at the ISAS Institute, who is now included in the JAXA space agency in Japan. The ISAS was led at that time by Professor Minoru Hoda, and ISAS was able to launch 1 mission per year with an annual budget of only $125 million. That approach of design to cost shows that, in fact, in the implementation of Horizon 2000, of these big red cubes and blue cubes, I had to include all the other missions which were already in development in order for them not to increase their cost and make it impossible to implement the program. This is why they were included in the program at the time of its formulation. The use of resources in laboratory and industry was an element of absolute success if we wanted to develop this program. A long-term plan like Horizon 2000 had the enormous advantage of offering all the scientists and engineers the possibility of becoming, for once, international leaders in their fields. In fact, it generated pride, motivation, thanks to the challenge of developing an ambitious program, instead of a series of individual missions, one after the other, competing against each other in a self-destructing approach. This approach has proven indeed to be an extraordinary, efficient tool of motivation and getting the best from all the actors and participants in the program. Every partner knowing where to go and how to organize the data. On top of this, a curious element which we experienced was that once we had decided what to do, in fact this diagram which I showed was translated even in Chinese and Japanese, we attracted international partners by the solidity and the willingness and the affirmation and confirmation that we were going to do this program. So the firmness of the plan was able to attract NASA, hopefully, because thanks to that cooperation, we increased dramatically the scope of the SOHO and the cluster mission, and later on of the Planck mission and several other missions that we have developed. The principle of this long-term plan for 20 years for the ESA science program was presented to the ministers of the member states in Rome in January 1985. Among the 13 member states of the European Space Agency at the time, there were enthusiasts about this program. I counted 4, if I remember correctly. Italy, at the time, very positive. Switzerland, always positive. Germany was very positive at that time, and Sweden. And there were a few grumblers, and I cannot avoid showing this picture of a lady which was instrumental in fighting against any expenditure at the level of Europe. I tried to convince her that she should look at the universe and that the modesty of our budget was essentially incommensurate with the richness and the wealthness of the universe. France and the United Kingdom were just accepting a small increase of 3% per year for 2 years. We were asking 7% for 10 years. So Hubert Curien, who was the delegate of France in the council, proposed a compromise, and the compromise was to reach 3% over 10 years, and then under the pressure of Switzerland and the positive people, Italy, Sweden, and Germany, we got 5%, real time, for 10 years. So we were very happy, and that started a big adventure. After 20 years, in fact 24 years, I will comment on that, all the cornerstones have been placed in orbit and more or less accomplished their promises, most of them. Only the Rosetta mission, the Comet mission, has not had a chance yet to demonstrate its scientific power because it has not yet reached its long-distance target, the Comet Churyumov-Gerasimenko. In addition, we have been able to develop 12 small satellites and 2 small missions, including the Smart 1 mission, which is a bit the record of the longest trip to the moon. It took 6 months to go to the moon with this mission, which was experiencing propulsion by electric propulsion. Furthermore, the safeness and stability inherent to the approach followed in Horizon 2000 has made it possible to reduce the costs of medium-sized missions by the use of recurrent platforms and systems. And that was the case for Venus Express, which benefited from the subsystem developed for its sister mission, Mars Express. That approach was also used for Integral, with probably more difficulties, in cooperation with the Russian Space Agency and the Academy of Sciences, through the reuse of the XMM, the X-ray cornerstone mission, and this is still in orbit. Another success of Horizon 2000 for Earth Sciences is that in 1977, the ESA Director General of ESA, Jean-Marie Luton, offered me the opportunity to frame the Earth Science program in a way similar to what had been done with Horizon 2000, and that led to the formulation of an envelope program in Earth Sciences called now Living Planet, which offers a regular set of scientific missions and explorers, like the Gautier mission, Cryosat, SMOS, ADM, Eloise, and Swarm, Earthscale, etc. Let me just come through now the highlights of this program, as we got what we wanted to get, and what success did we have, and what non-success did we have. Well, besides having offered many flight opportunities to all the partners of ESA in the science area, this included the scientists, science community, not only in Europe but outside Europe, industry, the ESA member states, and its international partners. The Horizon 2000 program has produced several side effects and benefits. The scientific harvest is abundant and unique. This is the picture of the Living Planet program. In the solar system exploration, on the 13th of March 1986, Giotto, the small satellite, spinning camera, we could not pay more than 80 million euros at this time, for the first time observed with high resolution the nucleus of a comet, and confirmed the model of Fred Whipple that the nucleus of a comet is in fact a dirty snowball. There was a big celebration of this encounter with Carl Sagan, Roald Sagdayev, who was also involved in this concert of missions to Comet, and Reimar Lustier on the picture. This was transmitted all over the world with more than 100 million people looking, and we had a great success. Finally, Europe, which a few years before had said we cannot afford planetary mission because they are too expensive, we made it with an 80 million mission, and we had the front page of all the newspapers. In the exploration of the solar system, Mars Express, a small mission which cost is probably less than $150 million today, has had a similar role in the rich harvest of results, in particular the confirmation of existing water on the surface of Mars and also early water, thanks to the Omega mission, the visible and infrared miragel mapping spectrometer that has made giant steps in showing that water existence of Mars very early and probably not in a permanent way for a long time. Thanks to ESA, the Cassini mission carried on board the Huygens probe, and Europe, thanks to that mission, offered, it's a small mission, the first image of the surface of Titan with centimeter resolution after a momentous long-distance and successful landing of a human-made probe on an extraterrestrial object, longest distance. Venus Express, the only Venus mission in orbit at this moment in time, has made dramatic contributions through various instruments on the study of the atmosphere of Venus. It probes, thanks to an infrared system and spectrometer, the upper and the lower layers of the atmosphere, and looking at why does the Earth's atmosphere, the Venus atmosphere rotates faster than the surface of the planet itself. It has had a tremendous impact on the study of the Venus South Pole vortex, which is very strange and changes its shape from day to day. And most interesting also has been the measure made on board of Venus Express of the sulfur dioxide concentration at 70 kilometers, which, according to my colleague Jean-Loup Berthaud, is probably due to strong emissions of SO2, most likely coming from volcanic activity. So we are not sure of that, but it's an enigma which probably requires more observations of Venus. But this mission costed very little, and thanks to the combination between this mission and Mars Express, we were able to do it. In solar physics and solar terrestrial relations, the SOHO cluster cornerstone, made of cluster, the 4 satellites cluster, and of the SOHO mission, remains a unique example of studies of the magnetosphere in 3 dimensions. With 4 satellites in the orbits in the magnetosphere, you have essentially an image of the magnetosphere with 4 pixels. It's not very much, but you manage to measure all the performances. This mission has also the very nice effect to make it possible to allow China, for the first time, to launch a scientific mission called Double Star, which has had a determining effect not only on the cluster science, but on the initiation of a very promising science program in China. This Double Star mission was the first scientific mission launched by China, and we are very proud of this. SOHO by itself has created a true revolution in solar physics, and the decision to make SOHO cornerstone triggered in the US several similar efforts. But let me show you an incredible picture, which was certainly what shocked me the most when I saw these pictures coming from SOHO, taken with the coronagraph. And you see on the right-hand side the keyboard, precision of the keyboard of the sun, which is the power spectrum of the oscillation of the sun, which I explained to Amaldi that they would help discovering the enigma of the neutrino problems. And on the left-hand side, you see stars for the first time circling around behind the sun, because the orbit of SOHO is in L1, between the sun and the Earth, and rotates around the sun like the Earth. And you see a very beautiful demonstration of the theory of Ludwig Wiegmann that comet tails are orientated always in the direction opposite to the sun because of the existence of a solar wind. Well, a few years after SOHO was launched in 1995, NASA resurrected its scientific program, and this is what I call the SOHO Revolution in the United States, and not only there, with the TRACE mission. You can see the result of that. Similar initiative was taken by the Japanese with the Hinode mission. The STEREO mission followed in 2006, 10 years after SOHO, and recently the SDO satellite provides a magnificent decent picture of the sun. I showed you one at the beginning. And more recently, a small group of scientists from Belgium and ESA decided that they could make a new approach to SOHO imaging and chronophotography, as I could say, through the development of the PROBA2 mission for a cost which is 10 times less than the cost of SOHO. So SOHO has created a real revolution, and we can be proud of having included it in the Horizon 2000 program. On top of this, I will not go through all the details, but we had great success with the Ulysses mission, first mission and only mission to travel above the ecliptic. We had marvelous results with the Hipparcos mission, which was the first satellite to make astrometric observations over the whole sky with the same instrument. Before it was done in the South Pole, in the South Hemisphere and the North Hemisphere, and the accuracy of measurements in the Southern Hemisphere were not as good as in the North. Now we have been able to increase the accuracy by a factor of 100. And the Hubble Space Telescope, to which we contributed 15% of the hardware. In fact, in result of that, we should have got 15% of the observing time. I was told recently that, in fact, we have got 30% of the observing time, so it was a very good investment, and I think we should be very happy with this. I could go through XMM Newton, the X-ray cornerstone, largest X-ray telescope launched, which is really challenging the community to understand how stars are born, and it has observed the youngest stars how the neutron stars are accreting matter and how black holes accrete stars around them. It's a real telescope for observing the violent universe. Herschel, with its 3.5 meter telescope, is the largest space telescope in orbit so far, and has, by itself, indeed, analyzed the formation of stars and has observed the youngest stars thanks to the new wavelengths and the new spectral range that it observed. It has also been able to detect water everywhere in the various objects of the universe. This is a spectrum where you see the abundance of lines from the water molecule in the Canis Majoris, VY Canis Majoris object. And surprisingly, the first image of an heliosphere outside the one in which we are embedded was done by Herschel recently. But most recently, the whole international astronomical community could admire the latest results by the small mission, a medium mission called Planck, not so small, but medium mission. This map is essentially 20 times more accurate than the previous one of the cosmic background at which the Americans launched, map. Well, the data of this picture are analyzed now. It took 1.5 years to get this map properly calibrated, and it shows many interesting features. First of all, it confirms without any doubt the scenario of inflation. You see the points on the curve. The curve is a model. The points with the error bars, the size of the points of the dots on this point are the error bars. So no doubt that the inflation model is absolutely confirmed. Most interesting is, in fact, what happens on the left-hand side of this curve, where you have a big divergence between the model and the points and the data points, which, of course, are also where you have the largest noise. So the next mission should understand what this happens. But apparently, the scientists involved in the development and the analysis of these results are very, very keen to analyze these data and to interpret them in terms of changing the nature of physical laws at the early stage of the universe. I cannot say more because this is certainly something which is going on, but in the future there is probably the need for such an instrument to fly again with higher accuracy for observing in this power spectrum the big scales of the universe which probably existed at the time of the Big Bang. Well, these are very beautiful successes. I think you can agree with me, and I am not modest on this type of things because I think we did a great thing. But we had a lot of problems. On the 28th of January 1986, the Challenger accident occurred, and this delayed the Ulysses, which was on the Ulysses launch, which was on its launch pad. Ulysses was supposed to be launched by the shuttle, and it delayed the launch by 4 years. The mission was eventually launched at solar minimum 4 years later, which was in fact a much better scientific situation for the observations, and it operated for more than 18 years. The Giotto spacecraft was lost in space at the time of the Challenger accident in 1986, and it was difficult therefore to use the JPL antenna, which were all concerned with the Challenger accident. But JPL, thanks to a very, very friendly cooperation, made it possible that we save Giotto. Hipparcos was put on the wrong orbit because its apogee boost motor did not ignite. And we had to face a situation where we leave the spacecraft in this orbit and try to get the best out of it or not. We did that, and in fact, we were obtaining better results than the nominal performance of the mission. The flawed mirror of the Hubble Space Telescope, you remember, it was not of the right shape, was in fact improved by the utilization of a system called COSTA, which was put on the Space Telescope by the astronauts, thanks to the European and American astronauts. Claude Nicollier, the Swiss astronaut, was in charge of the manipulating arm. And this system, which corrected the optics of the mirror, the pupil of the telescope, was able to correct properly the mission and restore the quality of the telescope. I could continue this long distance, but the most impressive and certainly the most shocking for many of us here was what happened on the 4th of June 1996, where this rocket called Ariane 5, in its first maiden flight, we were supposed to fly on the second flight of the rocket, but because the satellite, which was a telecommunication satellite, I think, was not ready on time, we were asked to move on the first flight. And unfortunately, 30 seconds after the launch, this is what we could see from the launch pad, from the viewing site. And that created a lot of problems, of course, a lot of drama, and I think it was absolutely essential that there is no other option in space science and in the Horizon 2000 program that we could not go for success. So success is the only option, failure is not an option, and we made all the efforts, thanks to the community, and many are here in this room today, thanks to the space agencies of the member states, to relaunch this mission 4 years later, thanks to 2 Soyuz satellites. And this leads me to the lesson learned, that in fact you should, that you should never give up. That was Baikonur, August 2000, and the team, which was really there for making this a success, really was happy that we got a success, and I finished the evening in the swimming pool of the hotel in Baikonur, with my dresses, of course. Well, thanks to the Horizon 2000, ESA has become the number 2 agency in the world after NASA in terms of the numbers of missions and quality of its mission in all domains of space science. This was a remarkable achievement. Well, you may ask, but why not number 1? Number 2 is okay, but number 1 is better. But, well, Europe is in fact number 1 in nuclear physics with the CERN, in ground-based astronomy with ESO. But I think that the main reason why we are not able to be number 1 in space science in Europe, it's because space is very popular among the member states and they want to have a big share of it. So every nation in the European Space Agency member states wants to have their own national program. And I think that in the US and in the USSR, at the time of its space glory, space has been essentially driven by military competition against the 2 superpowers, and not only by science. In Europe, on the contrary, the space effort was driven by science, 1/3, its direct civilian application, 2/3, and by a voluntary industrial policy, third. The creation of SOHO and ESA resulted as a post-war design, like I showed for CERN with Amaldi and Auger. These two people created the European Space Organization effort in order to preserve the reoccurrence of the war and make a peaceful cooperation among the member states. If that were competition, it was only scientific and industrial, not enough, unfortunately, to make Europe #1. Last point on my talk, could Horizon 2000 be reinvented today? Well, a few years in 1994, after we initiated, 10 years after we initiated Horizon 2000, we invented Horizon 2000 Plus, which included this time 3 cornerstones and a set of small missions. 2 of them are in development now. So we could have done it with a little less success because the missions were more expensive. And of course, the member states were informed of the tricks that we played with Horizon 2000, so they were very suspicious. So, but in general, could we today, in 2013, reinvent Horizon 2000? My answer is probably yes, in the principle and in the architecture of the program, but not exactly in the same form. Given first the growing ambition of the science community toward bigger missions and the new context of the world. The world of 2013 is not the world of 30 years ago, unfortunately, for space science, but the political, international, and financial context has deeply changed since 1983. In Europe, the financial resources for space remains more or less flat, at the same level since more than 10 years. And it is doubtful that the ESA member states will grant a substantial budget increase in the mandatory activities, particularly in the science program. So we have to live with what we have, and certainly it's not enough to make big things, but the approach taken by Horizon 2000 may inspire you on the way to do it. In the United States, the NASA situation is raising a lot of concern. Certainly in the United States, my American friends describe me how it is difficult, not only because the budget is stagnating since several years at more or less the same level also, and is now under sequestration, but also because NASA proves to be unable to manage big projects within affordable financial limits. The key example of that comes from the James Webb Space Telescope, whose cost has probably increased by a factor of 20 since its beginnings, and the launch has been postponed by more than 10 years. This project and the way it has been managed presents a dramatic illustration of that situation. And it seems, at least to me, that NASA has lost all capabilities to master the costs and schedules of its large flagship missions at the expense of delaying many other missions. In other words, NASA does not know how to manage any more of the missions which should justify its existence. So we have to reinvent space research. The US National Academy of Sciences regularly consults the scientific community in the preparation of the so-called Decadal Surveys in all disciplines. It's a very important element of the activities of the scientists in the United States. Some non-Americans participate in the activities of these groups. And here I show the 2 decadal surveys which were formulated, and the documents were released, I think, 3 years ago for the astronomy decadal survey, and 2 years ago for the planetary decadal survey. The plans that are proposed in these documents were unaffordable, impossible to implement the minute after the surveys became public. So, was it worth the effort? Was it a waste of time? I would probably say no. Not totally if the exercise is extended in the framework of the international context. So we have to invent a new global planning process. First, a new form of planning needs to be introduced in view of establishing a global Decadal Survey, if you want, a global science-driven roadmap based on the various individual Decadal surveys made in the US, in Europe, and in other countries. Recently, the COSPAR, Committee for Space Research, and the International Astronomical Union have understood that a planning exercise on a worldwide scale should become necessary. That approach was initiated for space in COSPAR, Commission E, and in IAU in ground-based astronomy. COSPAR set up a working group chaired by Pietro Ubertini in Commission E of COSPAR, involving representatives of the astronomy community from the main spacefaring nations and aiming at establishing this global roadmap that will be integrated within a similar program formulated by the AUI for ground-based astronomy and should result in a global decadal survey for contemporary astronomy. Of course, the implementation of these roadmaps should be in the hands of the space agencies, of the spacefaring nations, or groups of these. They already coordinate, these agencies, successfully their Earth observation missions within the Committee on Earth Observation Satellites, CEOS, also in the space exploration through the ISE-CGE and satellite navigation, without the necessity for intergovernmental agreements on budgets, which is, of course, a very difficult situation, as we have seen in the past on missions of even big size. So we should create in the world such an interagency group for the space science mission and the mission that EGU and several other organizations are interested in, which use space. This interagency group should involve the leading scientists and should also distribute upfront the leadership roles among the members of the agencies for the selected missions in the roadmap. Of course, this will require a new type of dialogue, dealing with mixed leadership. But we have seen that between ESA and NASA, where for a long, long time ESA was a second partner and always obeying the master, on cluster, SOHO and Planck, the situation was exactly the opposite. We had to teach NASA how to follow our rules and to work with us. It took some time of grumbling also, but after 6 months, our American friends are very good players. They accepted the game, and it was a great success. So this mixed leadership between agencies is something that we could consider. Furthermore, new resources may come from new partners like India, like China, and certainly Russia and Brazil, which are now internally in their own countries developing sophisticated technical infrastructures and are also in the process of formulating very impressive plans. Well, I think that the collapse which we may fear that may threaten space science could be avoided through some vision and political will, with a clear understanding and appreciation that national leadership of large space missions should now be shared among the partners, as ESA did in the examples which I just mentioned. Let me conclude this presentation by saying a few things. First of all, I am happy to have lived the past 50 years immersed in space science from the first rockets to satellites and balloons. I was very lucky. I have, of course, modestly contributed to the understanding of the Sun. I am very proud of having helped the scientific community in Europe and elsewhere in cooperating in a most peaceful activity driven by curiosity, need for discovery and search, increase in knowledge, and of course, possible aspects of education. I am preoccupied that the main nations presently do not act more willingly with vision and spirit, considering the enormous potential of offered by international cooperation. That's a pity. But we can change that, because what I would say is that if I look at the reason why we have been very successful in Horizon 2000, because all the partners were fighting to get this program done. Without the support of the scientific community, it would not have been possible. And the scientists always helped constantly. So many of you participate in this program in this room, and I would like to thank you so much for what you did. There are young people in the room, because I started this program when I was fairly young. I can share you with some experience which I had. If you are a young scientist and want to do something and to create something, and there are still opportunities to do that, you have to remain at the central core of progress by jumping over the barriers that you will find in front of you, political, administrative, financial. You have to find ways to jump above these barriers. And with cleverness, and the young people are very clever, you may succeed. You have to evaluate your constraints. Do not jump too far if you cannot jump too far, but you have to do that. You have to fight. There is no space science program without fighting, I can tell you, and you will experience that, I'm sure, and you have already probably experienced that. You have to resist temptations, not only the good ones, but the bad ones also, and you have to make sure that you already make your point together with your colleagues in front of the people who think that you are wrong. Never think that you can do everything by yourself. Space is always an activity which involves large number of people. The Planck, the cluster SOHO investigators can be counted by hundreds, several hundreds. The Planck article, the first article was published with 350 signatures or something like that, like in CERN, you know. So it shows how many people are involved. So you have to learn how to work with colleagues and collaborators. Sometimes not so easy, but with some intuition and the willingness to succeed, you may succeed. And you have to learn, and this is something which I learned myself, everybody in a team or in a program must be participating in it. Everybody has something to give, and you have to know what it is able to give. You may recruit a high-level polytechnician or engineer, and you think he will help you in this field, but finally he doesn't do that. But he is doing something else in another field. You may recruit a very low-level technician, and suddenly you realize that this technician is able to do many things that you could not imagine he was able to do. So you have to find where is this, what I call the golden nugget in everybody, make it shine and use it to make your program work. Through using the talent and the sense of responsibility that you will find in everybody, and if you manage to conduct these activities in a teamwork, you will be a very winning team and a strong leader. I would like to thank you all for what you did in helping the European Space Agency and all the participants in helping yourself also in making this program possible. And I hope I have convinced you that it's not impossible to do it again in a different way. And I think it's essential that the space organizations understand now that there is enormous amount of knowledge to acquire in the future with the new space missions, but this cannot be done in the same way as we had done before. And I think at the European scale we have shown that we could do something in a very adverse context, and the context is very adverse today, so there is optimism that we can come out of this mess. Thank you very much for your attention.
Thank you very much for 50 years of space sciences and your advice for the future, for the next 50 years. Find the golden nuggets in your team members and make them shine. These are very wise words. I would like to thank you for coming to this Cassini lecture, and thank you very much again for your presentation. Thank you.